Hi everyone, thanks for stopping by our poster. My name is Miguel Vallejos. I am a PhD student in the Petrol Engineering Department at the University Estadual de Campinas under the guidance of Professor Dennis and Guillermo. And today I'd like to share a bit about our research where we are developing a new method for fracture permeability upscaling. To give you a clear idea of what we are working on, fractures can generally be modeled in two ways: the dual porosity approach and the discrete fracture network, which I refer to as DFM from now on. The dual porosity model assumes that fracture have some simple characteristics like equal spacing, simple geometry, and uniform aperture. Because of that, dual porosity model is especially suitable for simple fracture system or regional faults. On the other hand, the DFM approach explicitly models fractures, capturing the variations in their properties, and this made it possible to realistically represent natural fracture reservoir. The challenge then is, how can we upscale DFM properties while preserving their original dynamic behavior? To estimate upscale effective flow properties of fractures, the most common methods used in commercial software are ODA, ODA corrected, and flow-based. The first one, the flow-based upscaling, is generally the most accurate, but it's also computationally expensive. The other method is much more efficient, but its accuracy drops when fractures are not well connected. The other corrected method was proposed to fix these issues, but according to the literature, it's only reliable within a limited range of fractures intensity. Some authors, like Hariri, argues that there isn't enough research available to fully support its accuracy. But if there are already three different methods for upscaling, why are we working on this? Well, as mentioned by Elfield and Geiger, half of the world's petroleum reserves are concentrated in carbonate reservoirs, and most of them are naturally fractured. The presence of these fractures creates preferential flow path. It means channeling with high anisotropy ratio, and because of this, choosing the right technique to upscale the permeability of the discrete fracture network model is vital for maximizing recovery from this reservoir. But as we said, every method has its own limitation, right? And usually forcing a trade-off between computational cost and accuracy. In this context, we aim to develop a machine learning model to predict the effective permeability tensors of fractures, overcoming the time and accuracy limitation of traditional methods. Train the model using DFMs with different levels of heterogeneity to ensure it's robust and widely applicable, both below and above the percolation threshold. Finally, our proposed model aims to achieve the higher accuracy of flow-based methods along with the computational speed of the other method, making it perfect for large-scale field simulation. In short, we are developing a machine learning method that's as fast as ODA but as accurate as flow-based. So how are we going to do this? Okay, basically, our model construction can be divided into four main stages, from data collection to final evaluation. First, we acquire the data for each discrete fracture network. We extract features like average fracture opening, fracture intensity, matrix permeability, and the number of fractures. Each set of these features is then associated with our target variable, means the effective permeability tensor, that will be calculated using a high fidelity method. The second stage is training the model, which is a supervised learning task. And this stage itself involves several key data preprocessing steps like feature selection. Here, we start by choosing a subset of the most relevant features, and we analyze correlation to identify which variables have the most impact on our target, which help us to avoid overfitting. Then we apply the logarithmic transformation for data with highly skewed distributions. This compresses the range of the values and helps normalize the distribution, which is important for the next step, the dimensionality reduction. In the dimensionality reduction, we use the principal component analysis, or PCA, to reduce the number of input features. The PCA combines correlated variables into a smaller set of principal components, as its name mentioned, and simplifying the model while retaining most of the original information. Finally, is applied a standard scaling to ensure that all features have comparable ranges, preventing variables with larger magnitudes from dominating the models. This is important because machine learning algorithms don't perform well when the input numerical attributes have very different scales. For instance, the linear regression is sensitive to the magnitudes of each variable, which can cause features with higher ranges to exert disproportionate influence on the model. After pre-processing, we trained several types of models. We used decision tree like random forest, XGBoost, catbots, as well as regression models with coefficient penalization like Rich and Lasso, and to further prevent overfitting, right? We also used the ensemble model voting regressor that combines the prediction from all the other models. In the third stage, we tested the models on a held-out test set, which was 20% of the entire data set, and we evaluated the results using 3 different metrics and 2 residual analyses. A model was considered successful if it achieved a satisfactory performance, for example, a coefficient of determination or R-squared greater than 0.9. Once we get a high-performing model, the final step was to apply it to our case study. We used it to predict the effective permeability tensors for the field model. Then, to validate our approach, we compared the simulated production curves from our machine learning-based model against the curves obtained using the traditional flow-based method. Our case study is a mount from field C, a geological model based on a naturally fractured oil reservoir in the Brazilian pre-salt. And the simulation model contains 48,000 active blocks and was run in CMG simulator using the black oil and dual permeability model with 2 wells, 1 water injector and 1 producer. Finally, our results or some important details. During the training stage, the hyperparameters were optimized with Grid Search CV tool. The key parameters too were the tree depth, number of estimators, and learning rate. The model trained with the random forest algorithm was able to explain 92% of the variance in the dependent variable. It means the effective fracture permeability of the test set employing the independent variables like matrix permeability, fracture aperture, P-third intensity, etc. from the training set. And during evaluation stage, as the flow-based method is computationally expensive and therefore recommended for grids with a small number of cells, our proposed method had to be tested using a small simulation model. At last, To quantify the similarity of the production curves, we use the normalized quadratic distance with signal, or NQDS indicator. NQDS value close to 0 indicates that the curves are very similar, and the production curves that were simulated with the model using the effective permeabilities estimated by the machine learning model are inside the 4% of acceptance respect to the reference results, which were simulating using the flow-based permeabilities. Okay, thank you so much for letting me to present my research, which is being conducted with the support by Shell Brazil, Energy Simulation, UNICAMP, and CEPETRO. Thanks to all of them for supporting this work. Of course, to CMG and SLB, Schlumberger, for providing access to the software licenses. If you have any question, please feel free to send me an email at the following address. Thank you.